Hello everyone, and thanks for watching Edupedia World Videos. In the previous video, we learned about the conservation of linear momentum, and in this video, we'll use that concept to apply to collisions. The basic concept we learned last time was the principle of conservation of linear momentum, which says that for a system, if the net external force or the sum of the net external force adds up to 0, then the net momentum, that is the sum of the individual momentums, is a constant, right? And we'll use this to the problem of collisions. So let's look at collisions in a slightly different perspective first. So let's assume I have a completely smooth floor, frictionless, and I have two objects, mass m1 and mass m2. And m1 is moving towards m2, right? And m2 has a spring attached to it. So while m1 is moving towards m2, eventually it's going to touch the spring, right? Once it touches the spring, the next instant it will move towards the right a little bit more, so the spring will be compressed. Since the spring is compressed, it will apply forces to get to its natural end. That is, it will apply a force on m2 towards the right and apply a force on m1 towards the left. That means m2 will start accelerating and m1 will start decelerating, right? And as long as the speed of m1 is greater than the speed of m2, the spring will go on being compressed. And as long as the spring is compressed, it will apply forces, which means m2 will keep on accelerating and m1 will keep on decelerating. There will come a point eventually when the speed of m1 and the speed of m2 will be the same, right? That is when the spring is at its maximum compression, right? So if there are two ends of the spring, this is moving towards the right with 10 meters per second and this is also moving towards the right with 10 meters per second. Then the spring is not being compressed or extended anymore, right? So it is both the length of the spring is a particular the compression is maximum. And after that, what's going to happen? The spring is still compressed, so it's still going to apply a force. So m2 will still keep on accelerating and m1 will still keep on decelerating. So there will come a point when m1 will detach from m2 and m2 will just move on forward and m1 will move with a much smaller speed. That is the essence of collisions, except there is no spring. So instead of this, if I take two balls and I make this ball move towards this ball will touch this ball, and if they're elastic, there will be a certain decomposition. So at one instant they might be like this, second instant they might be something like this. Both of them might be deformed, right? And they keep on increasing the deformation as long as they're moving towards each other. But then because they're elastic, the bodies will want to try to regain their original form, right? Spherical. So the deformation will be analogous to the spring and it will apply a force outwards on both of them and eventually they'll separate. Right. Now what is going on in this total process? If I take this combined both the objects plus the spring to be my system, there is no external force acting on this object. There is no external force in the horizontal direction, and in the vertical direction mg and normal will cancel each other, right? So the momentum of the combined system will be constant. And that is the principle of conservation of linear momentum, right? No external forces acting, the net momentum will be constant. So let's apply these to proper equations of collisions. So now I'm not going to use a spring anymore. That was just to try to explain to you. So let's say this is m2 moving towards the right with a v2, and this is m1 moving towards the right with v1, right? Completely frictionless and smooth floor. For a collision to happen eventually, v1 has to be greater than v2. That is obvious, right? If v1 is less than v2, then v2 will keep on going forward, v1 will go on slowly, and the distance between them will keep on increasing. So for a collision to occur, v1 will be greater than v2. Let's say the whole process of collision occurs, and eventually, finally, after the collision has occurred, m1 is going with the speed v1 dash, and m2 is going with the speed v2 dash. Now if this happens after the collision, this is the before and this is the after, then obviously v2 dash has to be greater than v1 dash. right? So if M1 and M2 collide, that means M1 is moving towards M2. And finally, after they've collided, if they're separating, that means M2 has to be moving at a greater speed than M1 so that the distance between them keeps on increasing. Distance initially decreases, distance becomes 0 when they collide, and distance keeps on increasing. The first thing to note is that there is no external force acting in the horizontal direction, so the net momentum will be constant in the horizontal direction, right? So the first equation which we will have is m1 v1 plus m2 v2 is equal to m1 v1 dash plus m2 v2 dash, right? Now the second equation is something which we'll assume for now. It only is true for a special type of collision called a perfectly elastic collision, and those are collisions in which the bodies are perfectly elastic. A perfectly elastic body is one in which when you compress or deform the body and then when you let go of it, it completely regains its original shape, right? So if you take a rubber band and you extend it and you leave it, it will go back to its original shape. If you take a packet of a ball of mud and you compress it, it will not go back to its original shape. So it's not an elastic body. So perfectly elastic bodies are those which completely regain their original shape. And we know that the work done by internal forces is related to the potential energy, right? And for completely elastic bodies, potential energy has to be the same initially and finally, since the complete configuration is the same, right? Potential energy depends on the configuration, how the objects are situated, how the particles of the system are situated relative to one another. So the final potential energy has to be the same. Hence, by conservation of energy, final kinetic energy has to be the same as initial kinetic energy. So the second equation would be half m1 v1 squared plus half m2 v2 squared is equal to half m1 v1 dash squared plus half m2 v2 dash squared, right? So these two equations are, this is conservation of momentum and this is conservation of energy, right? Now we can rearrange these two equations as, the second equation can be written as m1 times v1 square minus v dash square v1 dash square is equal to m2 times v2 dash square minus v2 square. This is the second equation. The first equation can be written as m1 times v1 minus v1 dash is equal to m2 times v2 dash minus v1 dash, right? And what this gives me is, if we divide these two, we'll get v1 plus v1 dash is equal to v2 plus v2 dash, right? Or we can also write it as v1 minus v2 is equal to v2 dash minus v1 dash. Right? This is the result which we've derived. By the way, these two equations, we know m1 and m2 and we know v1 and v2. Our problem was to find v1 dash and v2 dash. So two equations, two unknowns, we can solve and find v1 and v2 dash. I'm just trying to derive another result which comes from these equations, which is this, that v1 minus v2 is equal to v2 dash minus v1 dash. Now we know that v1 has to be greater than v2 for a collision to occur, right? So v1 minus v2 is the velocity of separation. Sorry, the velocity of separation is the second one. This is the velocity of approach. I apologize for that. v1 minus v2 is the velocity of approach. That is the velocity with which m1 is approaching m2. v2 dash minus v1 dash is the velocity of separation. That is, after the collision, the velocity with which they are separating. And we've derived from the conservation of momentum and conservation of kinetic energy that these two are equal, right? So this is the result which is true if conservation of energy holds. That is, it is true for perfectly elastic collisions, right? Now you can use these two equations and try to solve for the values of v1 and v2 at home. I'll just give you the values right now and I'm sure you can solve them at home. So v1, it's slightly complicated. v1 dash comes out to be m1 minus m2 by m1 plus m2 v1 plus 2m2 by m1 plus m2 v2, and v2 dash comes out to be 2m1 by m1 plus m2 v1 minus m1 minus m2 by m1 plus m2 v2. Right, so these equations, these formulas you don't need to remember. What you need to remember is the concept that how did we get them? By using conservation of momentum and conservation of kinetic energy. Right, and obviously we derive the result that velocity of separation is equal to velocity of force. So essentially we've solved the problem of perfectly elastic collisions. Right, and we don't need to have been given v1 and v2 to find v1 dash and v2 dash. Maybe we were given v1 dash and v2 dash and v1 and v2 and we wanted to find out the masses. We can find any two of these 6 quantities given the other 4 because we have 2 equations. Right, now let's move on to the more general type of collisions which are not perfectly elastic, in which the energy is not conserved. Right, so there can be many types of this. For example, if you throw a partially elastic ball at a wall, it will rebound, but it will not rebound to the same height. But if you throw a lump of clay to the wall, it will not rebound at all. So the things which will not rebound at all, which have a tendency to not regain their original configuration at all, are called perfectly inelastic. Inelastic. Opposite of perfectly elastic. And the things which, like a normal tennis ball, regain their deformation a little bit but not completely, the most general case, are called partially elastic. So you can have 3 types of collisions. You can have perfectly elastic collisions, partially elastic collisions, or perfectly inelastic collisions. Perfectly elastic collisions are the ones which we saw now and in which energy is conserved. Right? So how do we deal with the other 2? Well, there is another quantity which needs to be given to us, which gives us the second equation, right? Conservation of momentum, remember, will still be valid. Conservation of momentum only depends upon external forces, which are 0. Conservation of energy does not depend on external forces. It depends on the potential energy as well, right? The total energy will be conserved, but kinetic energy will only be conserved if the potential energy is the same initially and finally. That is not true always, right? So if that is not true, we need a second equation in place of that. So for that, we define a quantity E, which is called a dimensionless quantity, which is called the coefficient of restitution. And that is nothing but velocity of separation divided by velocity of approach. Right, this is E. And this is equal to 1 for perfectly elastic. We just derive that. For perfectly inelastic, it is 0. What happens in a perfectly inelastic body? Let's say I have one lump of clay on a table and I throw another lump of clay towards it. Both of them will join and move together with the same velocity. There will not be any deformation at all, right? So the velocity of separation will be 0 because they will not separate at all. For a partially elastic body, E lies between 0 and 1. So whenever you're given that a perfectly elastic collision is taking place, you can either use E is equal to 1 and use this as your second equation along with conservation of momentum as your first, or you can use conservation of momentum and conservation of kinetic energy. They'll give you the same answer because that is the method by which we derive this equation. Otherwise, if you're given a perfectly inelastic collision, you're given that E is 0. So in that case, the second equation you're given is basically V1 dash equals V2 dash, right? Because V1 dash minus V2 dash is 0. And if it's partially elastic, then you're going to be given a question such as two bodies collide in a partially elastic collision with coefficient of restitution equal to 0.5. In that case, the second equation will be velocity of the separation is half of the velocity of approach, right? So now we've learned how to solve problems involving any collisions. A couple of addendums to this. One of them is, what we saw was collisions in one dimension, that is collision along a line, right? M1 and M2 were initially and finally moving along the same line, right? But what if we have extended bodies moving along different lines? Let's say we have this object moving like this and this object moving like this, and when they collide like this, not head on. The collision which we saw earlier was head-on. This is not head-on. So in this case, the internal forces which are equal and opposite will be acting along this direction. And this direction is called the line of collision. So in such collisions, which are not head-on collisions but collision in two dimensions, collisions in a plane, all that you need to do is you need to take the components of the velocities along and perpendicular to the line of collision, right? Perpendicular to the line of collision, there will be no change in even the individual momentums. That is, in this direction, the momentum of this object initially will be the same as it is finally, because there is no force acting in this direction. Along the line of collision, on the individual particles, there are forces acting. Right, they add up to 0 if we take them as a combined system, but individually they have forces acting. So their velocities will change. So in such collisions, you take the line of collision, and along the line of collision you treat it like a normal head-on collision, and perpendicular to the line of collision you conserve momentum individually. Right. And a final thing, a concept which we need to learn called impulse. Right. So let's say I throw a ball at the ground. It touches the ground and it comes back up. Let's say just before touching the ground, its speed was v, and after touching the ground, its speed is also v. Like, let's say it's a perfectly elastic collision. So the change in momentum is 2mv, and it is upwards, right? Final minus initial. But what is the time during which this collision takes place? A collision takes place basically during an instant, during a very, very small amount of time, right? So even though the change in momentum is finite, the time taken is actually dt, right? And what is force? Force is delta p by delta t, which in this case becomes 2mv by dt, which is basically infinite. A finite quantity divided by an infinitesimal quantity. And that makes sense, because force is change in momentum per unit time. If you have a finite change in force happening over a very small change in time, you have to have a very large force acting on it, or basically an infinite force acting on it, right? So in this case, we don't talk about forces, we talk about something called an impulse. Impulse is represented by the letter J, and it is nothing but integral of f dt. Right? And since f is delta p by delta t, it is equal to the change in momentum. And the reason we do that is simply because we don't like infinites in our equation. So when such a problem occurs, in that there is a finite change of momentum in an infinitesimal interval of time, we don't talk of force, we talk of the impulse applied by the force. And the graph of the force versus time will be something like this. Right? A very small time interval, but a very large force acting on that time interval. Integral of f dt will be the area under the curve. And if you have a very small thickness, a very large height, the multiplication of them, the area can be finite. Right? And this is the change in momentum. So when you have collisions, or when you have any events in which a finite change in momentum occurs over a very small interval of time, we don't talk about the force, we talk about the impulse imparted by the force. And impulse is equal to change in momentum. So in this case, the impulse will be 2mv upwards. So we'll say that instead of saying the wall applies a force of infinite newtons upwards, the wall applies an impulse of 2mv upwards. Right? So this completes momentum. In the next lecture, we'll start learning about rotational dynamics. Right? And up till now, we've only talked about particles or systems of particles. We haven't talked about rigid or extended bodies yet. Now we are going to talk about rigid bodies, in which not only is where the particle located important, but how is it oriented important. That is, where is it facing, for example. For a point, it does not matter whether the point is facing towards north or east. But you have a rod, if the rod is facing towards north or east, those two are completely different problems. Right? So momentum and conservation of energy is complete now. In the next lecture, we'll start rigid body motion. Thank you.